大家好，我是 Lawrence Liu，欢迎来听今天的 PUF Academy Talk。Welcome to PUF Academy。今天的课大部分是会用英文讲 ，so 如果有什么问题，you're welcome to leave a comment on Facebook or a comment on the YouTube. So let's get started. So today's topic will focus on the design of PUF-based roots of trust. So this is today's agenda. We'll start off with some background about what is a root of trust. We'll discuss how a PUF-based root of trust differs from a traditional root of trust. We'll step through the design of PUFseucrity's PUFrt root of trust. And then we'll go through PUFseucrity's PUFcc crypto coprocessor, which is based on PUFrt. And then we'll briefly touch upon the available add-on accessory modules for PUFrt and PUFcc. And we'll finally conclude with a summary and a wrap-up. So first, we'll take a step back and look at the 5 primitive functions of cryptography. Each function establishes a different trust for a secure system. We have privacy, authentication, integrity, non-repudiation, and key exchange. Privacy establishes that a confidential message remains private, and that establishes the trust that the message is safe. It hasn't been stolen or eavesdropped upon. The function of authentication establishes the trust that the user is who they say they are and that their identity is true. Authentication is another way of proving that a user's identity is correct. Integrity establishes the trust that a message has remained intact and untampered with. Integrity checking confirms that a message has not been altered. Non-repudiation establishes the trust in the message sender's identity as well as the authenticity of the message. Non-repudiation proves the origin of a message as well as it guarantees the message's authenticity. And finally, key exchange establishes the trust that a key sent between two parties remains safe from leakage and theft. Key exchange is a method to securely share keys. So now we'll go into the main parts of the lecture, starting with what is a root of trust. Simply put, a root of trust is the implicitly trusted basis of a system's security. For trust to be established in a system, it needs to start from the root, or the root of trust. Next, using the 5 primitive cryptographic functions, as described in the previous slide, the other elements of system trust are established. For example, the function of privacy is used to build trust in system data by ensuring it is safe from theft and eavesdropping. To do so, ciphers are employed to encrypt important system data using a secret encryption key, such as a data encryption key. Since the most commonly used ciphers have been standardized by the US and China, these cipher algorithms are public knowledge, so everyone can see their inner workings, leaving the security of a cipher entirely dependent on keeping the encryption key a secret. And this is where a root of trust comes into play. As the implicitly trusted basis, it is either the source of the encryption key or the hardware unique key that is used to derive the encryption key. In much the same manner as with the function of privacy, the other primitive cryptographic functions are used to build the trust of a system from data sources kept safe by the root of trust, such as keys, certificates, and other types of data, such as passwords and code patches. So now that we've seen the types of data that a root of trust needs to keep safe, we will examine the basic architecture of a root of trust. Seen here, it is divided into 2 parts. One is for secure storage, and the other part is for key derivation. For secure storage, we safely store the types of data that we saw in the previous slide, such as keys, certifications, boot code, biometrics. And for derivation of keys that aren't stored in secure storage, we have a key derivation function along with dynamic and static entropy sources to derive keys from the source key. But keep in mind this is just a representative example of a root of trust. Not all roots of trust will look exactly as pictured here, but they should all share the same characteristics of being the source of implicitly trusted security elements for a system. And so now that we establish the trust in the system, what can we do with it? For example, a root of trust can anchor a chain of trust. In a chain of trust, the basis node here is used to establish a trust for the following node over here. And then that node establishes the trust for the next node down the chain, and so on. So for the first stage bootloader, we will have stored the signed certificate attesting to the authenticity of the second stage bootloader. So we can say we have a signed certificate that certifies that the second stage is correct. So that the first stage certifies the second stage. Second stage certifies the operating system. Operating system certifies the applications. So as you go down the chain for the secure boot, then everything is loaded in a trusted process. So this is where we see the important role of a root of trust, which offers both key storage and key generation to support the secure boot flow. So for a root of trust to play such an important role in a system process such as secure boot, it is important that the root of trust sits at the base of a system stack. So here we have an example of a system stack where you have the user, kernel, firmware, and hardware layers. And to act as the trusted basis, it is important that the root of trust sits at the bottommost layer, at the hardware layer here. And that's why you call this a hardware root of trust. Because in a system stack, to ensure correct operation, the basic assumption is that the upper layer relies on the lower layer working properly. So the applications relies on the operating system working correctly. The operating system relies on the hypervisor working correctly. So then as you go down, you see at the bottommost is the basis for the system stack to work properly. So therefore you need to put the root of trust at the bottommost layer. And so it only makes sense to implement the root of trust at the lowest level, which is the hardware level. And so that's why this talk is going to be about hardware roots of trust. That's why they have an H here in front. And a root of trust has become such an important concept in security that even ARM Holdings has declared it the foundation of cloud-to-edge system security. So that the PUFseucrity's PUFrt root of trust has been selected as an integral part of their reference secure subsystem, abbreviated as RSS, in the latest V9 ARM architecture. Here, in regards to confidential compute architecture, the CCA here. And also, again, to emphasize the importance of being a hardware root of trust, we see in the quote here from Brian Jeff, he uses he specifically uses the term hardware root of trust, not just root of trust. So that's basically background on roots of trust. Now we will go into PUF-based versus traditional roots of trust. And this table summarizes the differences between PUF-based and traditional roots of trust. First, we have internal versus external or conventional key provisioning. And then we have the cells are different, PUF-based cells versus a normal non-volatile memory cell. And then we have the secure storage methods versus basically no methods for secure storage. And then we have analog digital integration versus digital only solutions. So our remaining slides in this section will talk about each of these points in detail. So first, again, we'll start with internal key provisioning. And so we have without PUF a traditional roots of trust versus a PUF-based roots of trust. And traditional uses external key provisioning, while PUF-based uses internal key provisioning. And so as the PUF-based roots of trust, they rely on a PUF to generate the keys, as opposed to a traditional root of trust that uses an NVM for storage but doesn't have a way of generating the key. So that as a result, you need to have these extra parts of the environment and extra hardware to create the key and inject it into the NVM, such as an external random number generator, key management system, and the actual injection system itself, and also automatic test equipment. Whereas if you have a PUF-based root of trust, you can get away with, get rid of all these extra components and save time, save money, and also protect the key, because the key stays internal to your root of trust. It doesn't need to come from an external source and be injected in. So this is the first main difference between a PUF-based and traditional root of trust. Second is talking about the storage cell itself. For a PUF-based root of trust, we use anti-fuse technology. And for traditional roots of trust, they conventionally rely on E-fuses, which are simple and robust, but as you can see here from the diagram, this electron micrograph, it's easy to actually tell if the cell is unprogrammed versus programmed, compared to anti-fuse based or PUF-based root of trust, where the programmed and the unprogrammed cell is virtually identical to under examination under the microscope. So as a result, it's a lot easier to just reverse engineer any stored keys on a traditional root of trust by just examining it under the microscope. So no power would even be necessary to the root of trust. It can just decap the part and take a look under the microscope. So number 3 is the storage mechanisms, or not the storage scheme itself. We talk about the secure storage, and this slide here is talking in general about the entire anti-tampering features of a PUF-based root of trust. But if we talk about the secure storage itself, we take a look at number 3 here, which is a data address scrambler and also I/O shuffler, and that's based on the PUF, the built-in PUF, to randomize and obfuscate any stored data, so that it's not stored as plain text, it's rather stored as a ciphertext on a PUF-based root of trust. And this is unique because traditional roots of trust won't have a PUF, and so as a result they can't offer this ciphertext storage feature. And this slide also details the other anti-tampering features of a PUF-based root of trust, such as against invasive attacks, semi-invasive attacks, non-invasive attacks. And that's number 3 again for secure storage of a PUF-based root of trust. And finally, we move to the last, the difference between PUF-based and traditional, which is the digital versus digital analog integration. So first we start with a traditional architecture of a root of trust, which is digital only. So the sub-blocks here in black make up these are 3 different companies' root of trust solutions. And here the sub-blocks in black are each company's solution, which is implemented entirely in RTL, in digital logic. So the sub-blocks here in blue are actually analog blocks that need to be sourced from another company, such as an embedded NVM or PUF specialist, like eMemory. So that means for traditional roots of trust, such as the ones shown on this page, they need to undergo 2 rounds of integration. One, to integrate the analog blocks with the rest of the digital logic, and then again to integrate the entire root of trust with the system. And this leads to several disadvantages of an all-digital root of trust. First, the protections that were originally designed for a traditional root of trust, they do not automatically extend to cover those added analog blocks. So you can have anti-tampering features already designed into your digital logic here, but then once you integrate these analog blocks, they don't have that same automatic protection. And then two, the additional rounds of integration mean extra time for system integrators before that they can use the actual design itself, because you need to integrate the analog and then you can have to integrate the entire design. And then three, an analog dynamic entropy source is not easily obtained, so that system integrators often need to spend the extra time to design their own dynamic entropy source, such as ones here. So like if you have a random number generator implemented on your traditional root of trust, but you don't have a dynamic entropy source, then that's just another time and effort needed before you can use the entire root of trust, traditional root of trust. Contrast that to a PUF-based root of trust, which uses analog and digital components that are already integrated as one secure subsystem. So in this case, integration only needs to be done once, and that's with the PUF-based root of trust. And you don't need to deal with any proprietary interfaces. The system just sees one interface, the secure subsystem interface, and that can be like a digital APB, AHB, AXI, TCM protocol. The dynamic entropy source is already included in such a PUF-based root of trust inside the analog portion, so there's no need to spend effort creating that or trying to find a source for that. Okay, so now that we've gone over some background information, such as what is a root of trust and also the differences between a traditional and a PUF-based root of trust, we can dive into the two products we are going to introduce today. The first is PUFrt. So as I mentioned before, we have two products to introduce today. The first is PUFrt and the second is PUFcc, which we'll get into in the next section. PUFrt is a PUF-based hardware root of trust, and at its core is the secure storage based on the anti-fuse OTP technology, protected using entropy from the PUF and TRNG, all wrapped in anti-tampering designs, which were detailed in the previous slide. And then PUFcc builds upon the foundation of PUFrt by adding cryptographic engines to support a variety of security protocols. So again, we're going to focus on PUFrt in this section. We'll talk about design principles, the architecture, including the major blocks, and talk about operations supported and the key features. So here are the 4 design principles we used when building PUFrt. They are protect the core, multi-level protection scheme, making it easy to use and integrate, and also being a source of high-quality entropy. So here's the first principle again, which is protect the core. Security and trust in the system comes from the root of trust, and data stored in the core establishes this trust. Examples of such data are the hardware unique key, from which other system keys can be derived. Other examples could be the first stage of the secure boot flow, or the digest and/or digitally signed certificate attesting to the authenticity of a first boot stage. And such important data needs to be protected from unauthorized access and malicious tampering. Hence, the design of PUFrt must be focused on protecting the core data here in the OTP, upon which system trust is based upon. The second principle is multi-level protection. And attacks can come in many different forms, such as invasive, semi-invasive, and non-invasive. And it is better to have multiple layers of protection to fend off from the different types of attacks. So again, looking at the simplified diagram here, architecture, starting from the core OTP array, we use anti-fuse technology, which is more secure than eFuse-based OTP. We use obfuscated addresses and encrypted data derived from the PUF and TRNG entropy. We also use dynamic entropy enhanced reads to resist DPA, differential power analysis, and side channel analysis from using the dynamic entropy derived from the TRNG. And finally, we have anti-tampering designs implemented in layout and RTL, as listed in the previous slide. And these nested walls of protection offer the best defense against multi-pronged attacks. So the third principle is to make it easy. Even the most secure root of trust won't be useful if it is hard to use or difficult to integrate into a system. PUFrt has been designed to be both easy to use and easy to integrate. To make it easy to use, PUFrt comes with a comprehensive document package, including application note, integration guide, and testing methodology guide. In addition, API and firmware packages are available for quickly getting PUFrt ready to use with existing system software builds. And for ease of integration, PUFrt has been designed to support commonly used bus interfaces such as APB, AHB, and TCM. And PUFrt also comes with multi-platform FPGA versions to allow seamless integration with existing FPGA system emulation setups. And here we have an example of PUFrt being integrated into a system using dual bus, one APB bus for the main system bus, and then a separate private APB bus that can connect more securely to a secure subsystem, such as a separate crypto engine module for the SoC. And the final design principle of PUFrt is to use high quality entropy. And this is because modern cryptography depends on high quality entropy. As mentioned before, cryptographic algorithms are public knowledge, so their strength ultimately relies on keeping private keys secret. Because if it's guessable, a private key is not safe. Hence, a secure key is one with a high degree of randomness, especially so if it is to be used for deriving additional keys. Entropy also needed for providing masking bits to hide inner workings of security operations from side channel analysis. PUFrt provides both static and dynamic entropy sources, and certified using NIST standards such as detailed in Special Publication 822 and Special Publication 890b. PUFrt passes both of these statistical analysis tests. So thus, the final design principle of PUFrt was to be a high-quality entropy source. So here's a slide of the PUFrt architecture. It's a zoomed-in version of the architecture seen earlier in slide 15. The modules implemented in digital logic are dark yellow, and those by the hard macro in GDS are in light yellow. And the following slides will cover the major blocks in this diagram: the PRTC, the PUFtrng, PUFuid, PUF key storage, and the hard macro itself. So PRTC is the interface control module for PUFrt. User configurable, it can support a variety of standard bus interfaces, such as APB, AHA, and TCM. Using a memory mapped register interface, the PRTC allows PUFrt to be seen by system as a collection of system registers, so that accessing any of the PUFrt logic or hard macro functions is as familiar as reading or writing from a register. And PRTC is available in single and dual bus interface. With a dual bus interface, PUFrt can be hooked up to a private bus here that is connected to a secure subsystem for even greater data protection. Next, we have PUFtrng, which is the built-in true random number generator, comprised of a dynamic entropy source, which feeds a data whitener, also known as a PUF-based hash, using static entropy derived from the PUF, the NeoPUF. And PUFtrng's outputs have been measured to be compliant with the guidelines detailed in NIST's special publication 890b, which is used for estimating entropy quality. Next, we have PUFuid, which is PUFrt's source of unique identifiers, including hardware unique keys, or HUKs. By completely internalizing the key provisioning process, time and money is saved versus the traditional method of key injection in a secured clean room environment. The randomness of PUFuid's unique identifiers have been measured to pass the suite of statistical checks detailed in NIST's special publication 800-22 standard, with its Hamming distance measured to be close to ideal, if you compare the black to the blue squares here. And next we have PUF key storage, which is PUFrt's secured data storage system, created to protect private keys and other sensitive data. Instead of storing data as plain text, the data and address will go through an obfuscation process based on a portion of the individually distinct PUF, which is built into each PUFrt. Thus, when the same data is written to multiple PUFrt modules, the data will be completely different from one PUFrt to another, as the individual values of each PUF is unique to each PUFrt. And by comparison, here is one without PUF key storage, where the data looks exactly the same for each time it's written. The final block we will cover in this section is the hard macro, which makes up 1/2 of PUFrt in this diagram. Delivered in GDS format, the hard macro is sourced from eMemory, which is PUFseucrity's parent company, a world leader in embedded NVM solutions. The hard macro is comprised of a PUF and OTP array, which are based on the same anti-fuse technology, and the difference being that the PUF bit cell has 2 MOSFETs, whereas the OTP has just 1. So here we have the PUF bit cell with 2, and if you imagine, take 1 away, that's the OTP bit cell. So after PUF enrollment, half of the cells will be randomly programmed to a 1, and the other half to a 0, depending on which MOSFET develops the current path, either the left or the right. And so through this enrollment process, the cells in the PUF array are randomly populated with 1s and 0s. And that's how we get the static entropy source of PUF. So after seeing the different blocks and modules that make up PUFrt, we will now examine the different operations of PUFrt. Here's a list of categories of operations supported by PUFrt. We have data access, PUF setup, settings, access permissions, and the hard macro itself. PUFrt has been designed to be accessed as a set of memory mapped registers for the system to use. So basically, to perform an operation, a specific register is either read or written. And we will go over each of these categories and their individual operations in more detail in the following slides. So the first category is PUF data access operations. And these are to access the PUFrt data, which is stored in the OTP, the PUF, or the trng. For the OTP, with built-in PUF key storage protection, it has read and write accessibility. The PUF, from which the PUFuid unique identifiers are sourced, can only be read from. And finally, the trng is also only read-only. So random numbers from the random number generator are obtained through accessing the corresponding trng registers in the PUFrt memory map. And these operations are to set up the PUF array of the PUFrt for use. So the first one we have is quality check, which is done before the PUF is enrolled. Then we have enrollment itself, which populates the PUF with random values. Then we have health check, which is used after the PUF has been enrolled to check the quality of the PUF entropy. Next, we have the settings category. These are the option setting operations for PUFrt. So the first setting is for overprogram protection, which when enabled will first read the destination address to check if any of the bits have already been programmed. If so, then PUFrt will adjust the write data sent to the hard macro to inhibit programming at those already programmed locations to prevent overprogramming of the OTP array. And the second setting is test mode lock, which disables the test modes, in particular those related to the hard macro, as well as the ability to set any options such as this entire category of options. So once test mode lock is set, then these settings are all locked out. The third setting is PUF lock, which disables the PUF operations of enrollment and zeroization. And then the fourth and fifth settings are related to the shuffle, read, and write protection scheme, which is used in PUF key storage. And this setting enables or disables this protection scheme, such as in the case when the user would like to read and write data to the OTP as plain text for easier debugging during product development. This category of operations relates to access permissions. So the first operation is called secure range. This allows PUFrt to designate certain areas of the PUF and OTP array as secure or non-secure, so that only requests deemed secure by the system can access those secure areas of PUFrt, and non-secure requests are forbidden from accessing those same areas. The second operation is lock word, which allows the user to designate the access permissions of individual OTP locations, as small as 32-bit words, as read-write, read-only, or no access. And this way, the system could write data to the OTP, then later lock that location so that it can't be modified in the future. Now, the third operation is called post masking, which performs a similar operation as this lock word operation, except that post masking will set any access location to no access, and also that it's a non-permanent setting, so that when the power is cycled or PUFrt is reset, then any access permissions get set back to what they were before, as determined by the lock word here. And the final operation to restrict access to PUF OTP data is zeroization, which basically takes the OTP or the PUF array and writes all zeros. So that's the most extreme form of denying access by destroying the data, the original data. So now we come to hard macro operations. So the first one is to put the hard macro into sleep mode. It's a power savings mode, and because of the analog nature of the hard macro, there is a required wait time needed to put the hard macro into deep sleep mode, as well as the wait time to wake it up. And the second and third operations here are related, the off-cell margin read and also initial off checking. This operation is to check for initially bad cells. The only difference being that the first one here, off-cell margin read, checks an individual cell, and initial off checking checks for the entire array if there's any initially bad cells. And the fourth operation here in this category is on-cell margin read, which is to check for any cells that get weakly programmed. And finally, we have auto repair, which does an automatic scan of the entire array and repairs as many of the bad OTP locations as it finds, up to the limit of redundant cells available in the hard macro. So that's PUFrt operations, and now we'll just wrap up with the key features of PUFrt. So the digital RTL portion of PUFrt after synthesis is about 90,000 gate equivalents. But the hard macro size is dependent on the selected process node that PUFrt is manufactured in, since the process node will determine the PUF and the OTP cell size and charge pump sizes. And for interface, again, PUFrt can be configured as either a single or dual bus interface using a APB, AHM, or AHB, or TCM protocol. And in addition, there's an optional interface that can be made available just for the random number generator, so it can hook directly up to a separate DRBG, deterministic random bit generator. So this can be NIST 890A compliant, and the TRNG is 90B compliant. So when you combine those two, you can have a 90C compliant TRNG. And so the hardware unique key and the unique identifiers are about 256 bits in length, and there are 1 to 4 available depending on the configuration of the PUFrt. And the standard size of the OTP is 8 kilobits. Standard size of the PUF is 2 kilobits. And this can be customized depending on the customer's needs. And protection of secure storage is done through data shuffling, address scrambling, post masking, and secure range. So that's PUFrt wrapped up. So now that we've covered PUFrt, we'll go into PUFcc, and again with the same organization, where we go through the design principles, architecture, operation categories, and key features. So again, we have the PUFrt and PUFcc. PUFcc is the PUFrt-based crypto coprocessor. It builds upon PUFrt by adding cryptographic engines to support a variety of security protocols. And so this section is going to focus again on PUFcc. And we start again with the design principles of PUFcc, which are: use a PUF-based root of trust, be the trusted subsystem, data protection is paramount, and securely paired to the overall system. So the first principle is to use a PUF-based root of trust. Security and trust in the system come from the root of trust. And as a trusted subsystem, PUFcc needs to implement its own hardware root of trust, which is PUFrt in this case. A PUF-based root of trust supports internal key provisioning for the creation of unique IDs, HUKs, without the need to rely on traditional key provisioning methods. Internal key provisioning removes the need for a hardware secure module and secured cleanroom environment, which is traditionally used for key provisioning, which saves on associated costs. Ideally, the PUF used for internal key provisioning will not require post-data processing or helper data to maintain consistent key values over time and different operating conditions. And this is why PUFseucrity uses quantum tunneling technology for its PUF, which has been demonstrated to have near-ideal PUF properties with no aging effects. The second principle was that PUFcc is a trusted subsystem that is isolated from the main system. Sensitive and secure operations are offloaded from the main processor to be handled separately by PUFcc, freeing up the main processor to focus on other priorities. Easier to secure the boundaries of the smaller PUFcc subsystem than to secure the boundary of the entire system. And this is through the principle of hardware isolation. PUFcc includes all necessary components to run secure operations within its boundaries, protected by anti-tampering designs, which have been certified by third-party laboratories. The third principle is of data protection. PUFcc offers a full suite of cryptographic services and hardware accelerators to protect data at rest and while in transit. PUFcc's algorithms have been certified by the NIST Cryptographic Algorithm Validation Program, or CAVP. Security function of confidentiality is provided by both symmetric and asymmetric ciphers. Integrity checking is performed through checking hash digests or message authentication codes, known as MAC. And these cryptographic accelerators are built inside the anti-tampering protections surrounding PUFcc, which allow them to be completely isolated from the main system. And the strength of these anti-tampering protections have been independently verified through third-party labs using vulnerability analysis and penetration testing evaluations. Finally, the last principle is for PUFcc to be securely paired to a larger system, such as an SoC. PUFcc inside the SoC. APB and AXI or AHB standard bus protocols are supported by PUFcc to securely connect to the main system, such as through secured private channel. Secure non-secure operation separation is available if PUFcc needs to be integrated into a public or shared system channel. With its flexible integration methods for the pairing between main system and secure subsystem, PUFcc maintains the required hardware isolation to allow secure system operations to remain totally separate from normal ones. So this slide is a block diagram of PUFcc. And again, PUFcc is built by adding cryptographic engines, seen here, and a direct memory access module, seen here, to PUFrt, which is here. And so the following slides will cover the major blocks in this diagram, including PUFrt, the key vault, the dual bus interface, the two bus interfaces with the DMA, as well as the cryptographic engines. So starting with the root of trust, which is PUFrt in this case. As described previously, PUFrt integrates a secure storage, an OTP, the dynamic and static entropy sources of PUF and TRNG, and unique identifier generation, which is all protected by anti-tampering designs. PUFrt is a combination of hard macro and soft macro. So here we have hard macro, soft macro. And extending the soft macro portion of PUFcc to include cryptographic engines and the DMA yields PUFcc. So next we have the key vault, which is PUFcc's dedicated module for key management. It's comprised of a key array, a KA, for secure key storage, and key wrapping module, KWP, to support secure key exchange. KA has storage slots dedicated for session keys, private keys, and one especially for shared secrets. And the key wrapping module supports 3 different key wrapping modes to select from, such as AES, AES with padding, and AES with CBC. And notice they're all based on the AES cipher. PUFcc has a dual bus interface here, APB and then an AHB or AXI, along with a direct memory access. The APB is for connecting to the system bus to receive requests and send results out. The AHB or AXI interface is paired with the direct memory access module for fast access to system connected memories such as an SRAM or DRAM. And this diagram shows an example case of PUFcc being integrated into a RISC-V-based system with its associated memories. PUFcc can just as easily be paired with an ARM-based core instead of the RISC-V one shown here. So now we come to the cryptographic engines themselves. So a variety of ciphers, digital signatures, message authentication codes, hashes, and key derivation functions are supported by these cryptographic engines, such as a public key coprocessor, the block ciphers, stream ciphers, message authentication codes, hash, and key derivation functions. So the following slides will go through each of these blocks one by one. Starting with the PKC, which stands for Public Key Coprocessor. There are three different types of asymmetric cryptography available. So we have elliptic curve functions such as ECDH or ECDSA. We have SM2, which is defined by China's OSCCA organization with encryption, decryption, key exchange, and digital signature sign and verify. And finally, we have the classic RSA, which has key lengths of 1K, 2K, 3072, and also 4K bits, which support digital signature and verify. Public key algorithms such as these are categorized as asymmetric cryptography because the public key that's used for encryption is different than the private key which is used for decryption. Next we have the block cipher. Block cipher is also known as symmetric key cryptography because the key for encryption and decryption is the same. The block cipher block for PUFcc supports NIST's Advanced Encryption Standard, also known as AES, with key sizes of 128, 192, and 256 bits, with support with such regular modes as ECB, CBC, CTR, XTS, as well as supporting authenticated ciphers such as GCM and CCM. And China as well is represented here with the SM4 engine, supporting key and block sizes of 128 bits. Next we have a stream cipher block. Stream cipher works on the entire bit stream rather than breaking up a message into discrete blocks and processing each message one block at a time. And PUFcc has selected the Cha-Cha-20 engine with a key size of 256 bits and a nonce size of 96 bits, which has been standardized by the IETF RFC 8439 publication. And paired with the poly 1305 function, this can generate a message authentication tag so that the combination implements a authenticated cipher. Moving along, we have the MAC, the message authentication code block. And PUFcc supports both cipher and hash-based MACs. For cipher-based MAC, we are NIST Special Publication 838B compliant. And for hash-based MAC, such as the one shown for example here, we are FIPS Publication 198-1 compliant. And this diagram is a simplified showing the flow of generating a hash-based MAC, which takes the message along with two pads and the key and running it through a hash engine twice to generate the message authentication code. And talking about the hash engine, here we have the hash engine block, which PUFcc as well supports the US and China standards. US standard SHA-2, as detailed in the FIPS Publication 180-4 document, supporting 224, 256, 384, and 512, as well as the 512 variants, 512-224 and -256. And SM3 is is detailed in the document here, GMT 004 version from 2012. And now we get to the key derivation function module, which uses both key-based and password-based key derivation functions, as well as one- and two-step derivation flows. So here is a diagram of the two-step versus a one-step. So if using, for example, if we have a key-based KDF, the one-step flow uses the source key and directly expands it into the derived key. But if the source keying material, the entropy is deemed not sufficient, then we can go through an extraction step to get to an intermediate pseudo-random key, which then is used to expand into the derivation key. So the extraction step here can actually use the hash engine of PUFcc to perform double duty for extraction. And this expand function is used based on the guidelines set in the NIST publications 800-108 and 800-56C. Okay, so now that we've gone over the different blocks and modules that make up PUFcc, we will examine the different operations of PUFcc. And just like with PUFrt, here's a list of categories. We have PUFrt operations, key management, integrity authentication, private key cryptography, and finally public key cryptography. So starting with the root of trust operations, basically the PUFrt operations. These categories are the same as listed for PUFrt. So we're not going to go through each one again, but we can just go over the categories. The data access, the setup of PUF, option settings, access permissions, and hard macro operations. So these can be found in more detail in the section related to PUFrt. So for PUFcc specific operations, we start with the key management operations. And these are broken up into further categories of key storage, key wrapping, and key derivation. And these are the categories, and then these are the algorithms that they're based on, the reference standard, if applicable, as well as the description of each operation category. So key storage operations will write a key to either the OTP or the key vault, with the OTP storage having more permanence than writing to the key vault, which is primarily used to establish a common key storage location that all the crypto engines may access. Key wrapping operations use one of these three AES-based wrapping methods that was detailed in the key wrapping, the key vault slide previously shown, to securely import or export a key from or to PUFcc from an outside source. Key derivation uses either a key or a password to derive other keys, which is considered cryptographically secure and based on the special publication 800-108. So these next category are operations dealing with integrity checking and authentication. So for integrity checking, one can use a hash digest. You can hash the data before and after so that you can check using one of the modes of SHA-2 or SM3, which can be then compared with each other to find signs of modification or tampering. So either SHA-2 or SM3 can be used to create hash digests to be compared. And then another option is to use the MAC tag. So either using a cipher-based or a hash-based MAC algorithm to confirm authenticity. And again, these are the related standards to each of the operations that can be consulted for more details. Next, we move to private key cryptography. So this includes all of the private key-based ciphers on PUFcc. So there are three different types of ciphers here. We have ones based on AES, one's based on Cha-Cha, and one's based on the SM4, the China standard. And as mentioned in the architectural description of PUFcc, AES and SM4 are block ciphers, whereas the Cha-Cha is a stream cipher. And again, we have the related standards here that can be consulted for more details regarding the operation of each of these ciphers. And finally, we have the public key cryptography. So we have 3 types as well. We have elliptic curve, RSA, and SM2. The elliptic curve is based on the NIST standards, and SM2 follow these standards here, either the FIPS or the NIST special publications or the China-based GMT 003 document. And RSA is different because it uses Galois field as the algebraic basis. So with all 3 algorithms, they have the digital signature sign and verify operations. And key agreement and message encryption operations are supported by some, but not all 3. So for example, RSA only supports on the PUFcc only has the digital signature sign and verify, whereas the ECC has a more complete set of supported operations. So that concludes the PUFcc operations. We'll wrap up PUFcc here with some key features. We can start with the size. Depending on the configuration of the cryptographic engines, it can be anywhere from 350 to 550,000 gate equivalents. And again, with the PUFrt, the hard macro size is variable because depending on the process node, the OTP, the PUF, the charge pumps are all different sizes. The PUFcc is standard as dual bus interface with the APB for the system bus and the either AHB or AXI for the memory interface with the direct memory access. There is also an optionally available dedicated private bus if you want to securely export a private or a session key from PUFcc to like a dedicated crypto subsystem. So PUFrt is the root of trust that PUFcc is based on. And again, it integrates the OTP, the PUF, with the PUF key storage, secure storage system. And it includes the TRNG with the SHA-2 or PUF-based data whitener, as well as health checking to monitor the entropy coming out of the TRNG. And PUFcc has a suite of cryptographic engines, such as your asymmetric keys, cryptography, such as based on elliptic curve, ECC, or SM2, or Galois field, RSA, as well as the symmetric key ciphers, AES and SM4. And then hash engines, again, SHA-2 and SM3, and password-based, key-based, key derivation, as well as 2 types of MAC generation, either cipher-based or hash-based. And for integration into a system, PUFcc requires the use of external SRAMs mostly for the PKC coprocessor, for the internal use, public use, and the key array use. And to help with integration, we have a software development kit with APIs, firmware, and sample code to help get you integrated as quickly as possible and running simulations as soon as possible. So that concludes PUFcc. This next section, we're going to move on to some add-on modules mostly for memory support protection. So these are the memory protection solutions offered by PUFseucrity. We have PUFEF, which is a module created for protecting embedded flash, which is based on the PUFrt root of trust. We have PUFenc, which is an add-on module designed to work with PUFcc. and it's targeted to protect external NAND flash. And then we have PUFxcc, which is also designed to be a PUFcc add-on module, and that's created to support execute-in-place instructions from an encrypted NOR flash. And so now we'll go into just each of these very quickly, starting with PUFef. PUFef integrates a secure embedded flash, an eFlash controller, and a lightweight cipher, along with PUFrt. And this extends the protections of PUFrt to cover the embedded flash. And this allows the embedded flash to be accessible with the same APB interface that the OTP, PUF, and TRNG that PUFrt uses. So the embedded flash is protected again by a lightweight cipher. It could be RC6 or AES Lite. And this will support execution in place of protected code stored on the embedded flash. So that's PUFef, stands for embedded flash. PUFenc is made for NAND flash asset protection stored on the NAND flash. So this doesn't include the NAND flash. This is just a sort of a add-on module to PUFcc, which is here. And PUFenc adds an AES GCM cipher engine, which supports authenticated encryption and decryption for asset protection and tampering detection. And this binds the MCU and external flash with a device unique key. The device unique key, of course, is derived from the PUFrt root of trust embedded inside PUFcc. And this is considered locally keyed protection. We say local because each PUF, again, has a unique value. So each PUFenc unit is a unique locally protected key. And so this process we call from global to local key switching. It allows for asset protection at the individual die level, which makes it independent of any globally assigned factory key. Then we get to PUFxip, which is for NOR flash asset protection. XIP standing for execute in place. And this adds a XTS cipher engine, which is well suited for protecting sector addressable data. And a fast XTS engine paired with a fast NOR flash allows for direct execution of encrypted code. And the data encryption key, which is derived from the hardware unique key, ensures total privacy, as the key source and derivation process remain completely internal to PUFcc and PUFxip, which is the internal key provisioning we talked about before. All right, thanks for sticking out with me till the end. So we only have one last page for the summary to cover, and that's it. So here's a one-page summary of today's talk. Cryptography and security are based on trust. And how is this trust established? It's established from an implicitly trusted basis used to authenticate the other components code of a system. And a root of trust, ROT, is such an implicitly trusted basis. A root of trust can anchor a chain of trust that forms a secure, measured boot flow. And PUF-based roots of trust offer benefits over ordinary roots of trust, such as internal key provisioning, integrated digital and analog solutions. And PUFrt is one such PUF-based root of trust. From PUFrt, we can create a PUFcc, which is the crypto coprocessor, by adding cryptographic engines to PUFrt, the root of trust. And then we have extra accessory modules for memory protection. So we have PUFef for embedded flash protection, and that's created from PUFrt root of trust basis, adding an embedded flash with an eFlash controller and a lightweight cipher. Then we have external flash asset protection, such as for a NAND flash. And that's created using an accessory module called PUFenc. And that's added with PUFcc to give protection for any assets stored in external NAND flash using AES encryption. And then finally we have PUFxip, which is an accessory module again for PUFcc to give external flash with execute in place capabilities from an encrypted NOR flash for faster access speeds. So there you have it, PUF-based roots of trust from PUFseucrity. So thanks again. If you want to find more information from PUF Academy, here are 2 links for Facebook and YouTube. Hope you got something useful out of today's talk, and have a great day. Thanks.